Hello seniors, today we're going to see electronic assignment number 5, which is about equations of tangent and normal lines. As we have seen in the previous classes, we already know how to differentiate a function, right? And we know the concept of the derivative or differentiation of a function, which is the gradient or slope function of a given function at a given point, okay? That's the basic definition of a derivative, right? And now we're going to see how we can use that concept in order to find the equations of both the tangent and normal lines to a curve at a given point. Okay, so equations of tangent and normal lines. The objective for the class: draw tangents and normals to a curve and find their equations. So before we start with the specific topic, we're gonna review what the equation of a line is about. If you remember, there are two main ways in which we can write the equation of a line, right? The first one is the slope-intercept form, which is this one, y equals mx plus c, where m represents the slope or gradient of the line, and c represents the y-intercept, that is where the line crosses the y-axis. Then we had the point slope form, which is written this way: y minus y1 equals m times x minus x1, where m is also the slope or gradient, and x1 and y1 are the coordinates of a given point of the line. Okay, so the difference between both forms is that in this form we see the y-intercept directly, and in this case we have a known point just by observing the equation of the line, right? So we can use either to solve these types of problems, but normally we would use this one as it's the one we're most used to work with, right? Okay, then we have the concept of parallel and perpendicular lines. Parallel lines are lines that won't ever intersect, just as you can see here. This is how we symbolize parallel lines. Line P is parallel to line Q, right? Line P is parallel to line Q. And when two lines are parallels, we say that they have the same slope, right? That is a condition of two parallel lines. Then we have perpendicular lines, which is this case over here. And perpendicular lines are lines that intersect forming a right angle. Remember that right angle means that they form 90 degrees. Okay, so we say that line S is perpendicular to line T. And in the case of perpendicular lines, remember the properties for the slopes. We say that the slopes of two perpendicular lines are negative reciprocals. So if, for example, the slope of S is, let's say the slope of S is 2, then the slope of T would be negative 1/2. We flip the number and we change its sign, right? So that's how we find the slopes of perpendicular lines. You can also remember it this way: a slope of the first line times the slope of its perpendicular line is always equal to -1. These properties are not in the formula booklet, so you should remember this. Okay, so then we have a definition. The normal line at a point in a curve is the line perpendicular to the tangent line at that point. Okay, so in previous classes we have already seen what the tangent line is, right? The tangent line at this point, for example, is a line that touches the curve at exactly that point, right? And it does not touch it in any other interval, unless this function, for example, does something like this, and then this line extends, and then it touches the curve at another point. But the idea is that at this specific point, it should barely touch, we would say, le peina to the curve at that point, right? So that's a tangent line. And the normal line is just the line that is perpendicular to that tangent line at that same point, right? That's the concept of a normal line. Okay, so this is the most important part of the class: the steps to find tangent and normal lines to a curve at a given point. And here you'll start seeing how we can apply the concept of derivatives in order to find these lines. And later on you will see other types of applications of this, which are more interesting. So, steps to find tangent and normal to a curve at a given point. The first step is to find the derivative of the function. Why do we do that? Because the derivative represents the gradient or slope function of f of x. Then, step number 2, we substitute the x-coordinate of the given point into f prime of x, into the derivative function. Why do we do that? Because that gives us the gradient or slope of the tangent line at the given point, okay? So if we replace the given value of x, which we're going to see with exercises later on, into the derivative function, we're going to get the value of the slope of the tangent line at that point, okay? So and the slope is equal to the derivative function evaluated at the given value of x. Okay, so with this step we already have the slope of the tangent line. Then it says substitute the given x value into the original function f of x. So instead of replacing it into the derivative function, we're now replacing it into the original function. Why do we do that? Because that gives the y coordinate of the given point, right? If we replace the value of x into the original function, we're getting the y coordinate of the point. So we already have both the slope of the tangent line and a given point, right? Sorry. And a given point which is xo, yo, right? The given point. So once we have the slope of the function in a given point, I can already find the equation of the line, which is exactly step number 4. It says substitute the point into the equation of a line, which is y equals mx plus c. I already have the value of m, which I found in step number 2, and I already have the values of y and x, which I found in step number 3. So with those information, I can find the value of c and finally determine the equation of the tangent line. Okay, so it says this gives the equation of the tangent line through xo, yo. Once I have the equation of the tangent line, I can find the equation of the normal line. How? It says to find the equation of the normal line, use the same method, but using -1 over m as the slope. In step number 2, we found the value of the slope, so we just find the negative reciprocal of that value in order to obtain the slope of the normal line, and then we replace it with the same given point, which is xo, yo. Why? Because both the tangent and the normal line share this common point, which is basically xo, yo, right? So if they share the same point, then I can use that point in order to find the equation of the normal line, right? Which I could use, again, this equation over here. I replace the values and I find the equation of the normal line. Okay, so let's see these steps applied into different problems. You'll see that this is very easy. The steps are actually very intuitive. There's no need for you to memorize these steps. You see that as you go on with the exercises, you would kind of know what step you should do next in order to get to a result. So let's see. It says write an equation for each line, and in part A it says the tangent line to the curve f of x equals x squared plus 1 at the point 1 and 2. Okay, so we're given the point already. We already know x, we already know y. This would be xo, yo, right? Okay, so if we follow the steps, the first step says that we need to find the gradient function, right? We need to differentiate the function. So first of all, let me copy the function f of x equals x squared plus 1. And now I'm gonna differentiate this. F prime of x would be equal to, we already know how to differentiate, this is 2x. 2x plus 0, right? So there's no need to write the plus 0 here. Okay, so we already did the first step. We have the gradient function. Second step. The second step says substitute the x coordinate of the given point into the gradient function. So we're going to substitute the x coordinate, which in this case is 1, into our gradient function. So we're going to find f prime of 1 in this case, which is 2 times 1. So f prime of 1 is equal to 2. And this value we obtain here is exactly the gradient of the tangent line. So from this information, we're going to say that the slope of the tangent is equal to 2. right? Okay, so we already have the slope of the tangent line. Then we go to step number 3. Step number 3 says, substitute the given x point into the original function f of x in order to get the y value, right? But in this particular exercise, we are already given the value of y, right? If we substitute the value of x into the original function, you will see that we will get 2, right? Because it will be 1 squared plus 1, and 1 squared plus 1 is 2. So we are already given the value of the y coordinate in this case. In other cases, we're not given, for example, in this one, the next one, we're only given the x value, so we need to find the y value. But as we're given the point in this case, we're just going to say that the point, the known point, has coordinates 1 and 2. And that's fine, okay? So we already have the slope of the tangent, we already have a known point for where the line passes. So I am able to now find the equation of the tangent line, which is exactly for the 4th step, right? It says find the equation of the tangent line. So I'm going to write the general form, which is y equals mx plus c. I already know m, and I already have the given point. So I'm going to substitute those values, and I'm going to say this is equal to 2 equals 2. The slope is 2, x is 1 plus c. So here we obtain the value of c, which is c equals 0. So finally, the equation of the tangent line is y equals 2x. This is the equation of the tangent line we are looking for, right? So this is the final answer. We just wanted to find the tangent line. It does not, for this exercise, we don't want to find the normal line yet. So this will be the final result. Let's see what happens when we do this graphically. You may want to do this in your calculators if you want. I'm going to draw this function using Desmos, and I'm going to draw the function and the tangent line. And this is just to verify that the procedure we're doing is correct. So if we go to Desmos, I'm going to draw the function x squared plus 1, and then the tangent line, which has equation 2x, y equals 2x. So there you have, you see that we get a parabola and a tangent line. If I plot the intersection point, you see that that's exactly the intersection point we were given in the exercise, 1, 2, okay? So you see that this works, this method works. We're finding the tangent line at a given point, which is 1, 2 in this case. Okay, so I'm going to put the sketch. I have it here. This one. I'm going to take it up just for you to have a graphical representation of what's happening. I'm going to put it there. There you go. Okay, so this is correct. Then we're going to do exercise B. It says, find the normal line to the curve f of x equals 2 root x when x equals 9. So I'm going to copy the information. It says f of x equals 2 square root of x for x equals 9. That's what I want to find. Okay, the normal line. In this case, I am only going to find the normal line. So you'll see that we're going to follow exactly the same steps. The first step is to find the gradient function, right? The gradient function, which is a derivative of this. So before doing that, I'm going to rewrite the function like this in order to be able to differentiate. 2 times x to the power of 1/2. So now I'm going to apply the derivative f prime of x, and this would be equal to 1/2 times 2 times x to the power of 1/2 minus 1. I assume that you already know how to differentiate. Okay, so if we reorganize this, we see we can simplify the 2's. So we're going to have f prime of x equals x to the power of negative 1/2. X to the power of negative 1/2. And x to the power of negative 1/2, if we want to write this in a more elegant way, is the same as saying 1 divided by root of x. Okay, so this is a gradient function. Okay, once we have the gradient function, we want to find the value of the slope, right? As we're evaluating this function for x equals 9, then to find the value of the slope of the tangent at this point, I have to replace this value of x into the gradient function. Okay, so I'm going to find f prime of 9, which is equal to 1 over root of 9. And 1 over root of 9 is equal to 1/3. 1/3. That means that the slope of the tangent, m tangent, is equal to 1/3. But if you remember from the exercise, we're looking for the normal line, not the tangent line. So I'm going to find, with this information, I can already determine the slope of the normal line. The slope of the normal line is a negative reciprocal, so slope of normal line. The negative reciprocal of 1/3, that's negative 3 over 1, we could write, right? Which is the same as saying negative 3. So we already have the slope of the normal line. Once I have the slope of the normal line, I need to determine the given point, right? I already have the value of x, but now I need to determine the value of y for this value of x. So how do I calculate that? I'd replace the value of x into the original function. Okay, so I'm going to find f of 9. So I'm going to replace this into the original function. This would be equal to 2 times the square root of 9. This is equal to 2 times 3. 2 times 3. So f of 9 is equal to 6, right? So the given point has coordinates, 9 in x and 6 in y. Okay, and we already have the slope of the normal line. So once I have the slope of the normal line in a given point, I can find the equation of the normal line. So we're going to write the general form, which is y equals mx plus c, and then we're going to replace the known point and the slope into the equation. So this would be equal to 6 equals negative 3 times 9 plus c. If we solve this, this is 6 equals negative 27 plus c. So the value of c is equal to 6 plus 27, that's 33. Okay, so finally, the slope of the equation, let me write here, this is equation of tangent line. There. And here we're finding the equation of the normal line, which would be, I'm going to write here, y equals negative 3x plus 33. This is the equation of the normal line. I'm going to write it here. Equation of normal line. Let's see what happens when I graph this. So I'm going to graph the original function and the equation of the normal line to see if this is correct. So 2 square root of x and negative 3x plus 33. I'm going to go to Desmos. I'm going to erase this. The first one is 2 root x, 2 times the square root of x. And the equation of the normal line is minus 3x plus 33. And you see what happens, right? We have the curve and a line that is perpendicular to the tangent line at this point, which is 9 and 6, which is exactly the point that we were given for this exercise, right? So you see that this works. We found the equation of the normal line to this curve at this point, 9, 6. So let me go back. I'm gonna paste the image here. This one. I'm gonna put it right here. There you go. Okay, so that's it for exercise B. Now we're gonna go to exercise C. Exercise C says, find the equation of the tangent and normal lines to the curve f of x equals x plus 27 over 2x squared when x equals 3. So we're asked to do the same thing, but now we're going to find both the tangent and normal lines. So you'll see that the process is exactly the same. So let me copy the function down here. So f of x equals x plus 27 over 2x squared at x equals, I think it was 2, x equals 3. Okay, at x equals 3. Okay, so the first step is always find the derivative of this function. So we're going to find, first of all, I need to rewrite this function, rewrite it as x plus 27 over 2 times x to the power of negative 2. Okay, and then I find the gradient function, f prime of x equals, the derivative of x is directly 1, and this would be minus, because of the negative 2, minus 27 times 2 divided by 2 times x to the power of negative 3, assuming that you already know how to differentiate. Okay, so I see I can simplify the 2's. So this would be, if I rewrite this, this would be f prime of x equals 1 minus 27 divided by x cubed. Okay, so we already have the gradient function. Once we have the gradient function, the second step is to find the value of the slope. How do we do that? We replace the given value of x into the gradient function. Okay, so I'm going to find f prime of 3. F prime of 3 is equal to 1 minus 27 over 3 cubed. 3 cubed is 27, that means we can simplify this with this, and we get 1. So this is equal to 1 minus 1. That means that the gradient of the function at x equals 3 is equal to 0, right? That means that the slope of the tangent line is equal to 0. If you remember from when we studied lines, whenever we have a line with slope 0, we're talking about a horizontal line, okay? So we should know by this information that the tangent is a horizontal line. So I'm going to write it here, horizontal. Now I'm going to write it later when we find the equation. Okay, so m tangent is 0. What will happen to the slope of the normal if the slope of the tangent is 0? The slope of the normal line is a negative reciprocal, right? But the negative reciprocal of 0, we write 0 over 1. The negative reciprocal would be negative 1 over 0, right? But this number is undefined. Remember that any number divided by 0 is undefined, but we know it's infinity, right? That means that the equation of the normal line would be a vertical line, right? If the tangent is a horizontal line, then its perpendicular would be a vertical line, right? Which is, and vertical lines, remember, have a slope of infinity or undefined. Okay, so let's keep on with this. Step number 3, we need to find the y coordinate of the point, right? Of the point of intersection. So how do we do that? We replace this value of x into the original function. So we're going to find f of 3, which is equal to 3 plus 27 over 2 times 3 squared, and this is equal to, let's do this here, 3 plus 27 over 2 times 9, that's 18, and we can simplify this. If we divide both by 9, this would be 3 halves. Okay, so f of 3 is equal to 3 plus 3 halves. 3 halves is like saying 1.5. So f of 3 is equal to, this would be 9 over 2 or 4.5. Both results are fine. Okay, so we have, this is actually not a final result. So we already have the given point. So the point has coordinates in x, it's 3, and the y coordinate is 4.5. I'm going to leave it as the decimal. Okay, so we already have the slope of the tangent, and we already have the given point. That means that I can go on to step number 4 and find the equation of the tangent line, right? The equation of the tangent line would be y equals mx plus c, as always. We already know the value of m, which is 0, and we have the given point, which is this one over here. So I'm going to replace the values, and it's 4.5 equals m is 0 times 3, which is the value of x, plus c. So you see that here we get the value of c, which is equal to 4.5. So finally, the equation of the line would be y equals m is 0, so 0x plus 4.5. So this is the same as saying, let me put this a little bit upper. So this is y equals 4.5x. 4.5 only. And you see that this is the equation of a horizontal line, right? It is independent of the value of x. So this is an equation of tangent line. And I'm going to write here horizontal line. Okay, so we already have the equation of the tangent line, but now we need to find the equation of the normal line, which is step number 5. In this case, as the tangent line is a horizontal line, you should know that, okay, so if I write y equals mx plus c to find the normal line, you should know that the normal line should be a vertical line, right? Whenever we have a vertical line, remember the structure of a vertical line. It's directly x equals something, right? And if we know that the vertical line should pass through the point 3 and 4.5, then this value of x corresponds to the equation of the vertical line. So the vertical line is directly x equals 3. And that's it, right? This is the equation of the normal line. Remember, slope is undefined for a vertical line, so we write it directly as x equals something to represent the vertical line. So this is the equation of a normal line, and it is like this because it is a vertical line. So this is a particular case, people. Do not think that the tangent line would always be horizontal and the normal line will always be vertical. This is a particular case. Actually, in the exercises before this one, we got normal lines which were not vertical and tangent lines which were not horizontal, right? Okay, so we have the equations of both. Let's see what happens if I plot the original function, which is this one over here, the original function, and both the tangent line and the horizontal line. Let's see what happens. So I'm going to plot x plus 27 over 2x squared. X plus 27 over 2x squared. So that's the function. Then I'm going to plot the horizontal line, which was y equals 4.5. So y equals 4.5. You see that we get a tangent line there, which is horizontal. And I'm going to plot the vertical line, which is x equals 3. And you see that we get a normal line at exactly the same point of intersection, which is the point 3, 4.5, which is the point that we found. So you see that the red line, the horizontal or tangent line, is perpendicular to the normal line, which is a blue one. And here you can see that although this is a tangent line at 3, 4.5, the red line still intersects the curve at another point, but that doesn't matter. The concept of tangent line is that it should touch the line at one point and only at that point for that particular point, okay? Le tiene que peinar en ese punto, ¿sí? No importa que le corte en otro lugar. That's basically the concept of a tangent line. Okay, so I'm gonna put the image here. I think this is clear enough. I'm gonna put it here for you to see the graph. Okay, we're still left with one last exercise, which is part D, but I see that this video is becoming too long, so I'm gonna leave the video here and I'm gonna solve this later on, and you can try solving this on your own to try and see if you really understand this, and then check your result with my resolution, which will be down there when you check the assignment. Okay, so that's it. Next week you're gonna practice with lots of exercises about this, but we're getting into the interesting part of derivatives, and I hope this was clear enough for you, and if not, please let me know your doubts. See you, seniors.